Thank you very much for your very kind introduction. My name is Fengxia Hu. My first name is Fengxia. The surname is Hu. I come from Beijing, from Institute of Physics, Chinese Academy of Sciences. I work together with Professor Baogeng Shen. He is an academician of Chinese Academy of Sciences. We work together. The title of my talk is Magnetocaloric and barocaloric effect for efficient energy conversion. Firstly, I talk about what's the caloric. Actually, for the ferromagnetic materials, the spin ordering driven by the magnetic field can produce a magnetocaloric effect. For the ferroelectric materials, the polarization ordering driven by the electric field can produce the electrocaloric effect. And similarly, for the ferroelectric materials or the general materials, the lattice ordering driven by the pressure can produce the barocaloric or the elastocaloric effect. The calorics has many applications. For example, the caloric can be used for cooling, can be used for the heat pump, can also be used for the thermal management for chips and deep space, can also use for the waste heat recovery, and also for the thermal magnetic power generation. So in China, we have a caloric committee. This committee is attached to the Chinese Society of Rare Earths. This committee was set up at the year of 2019. The director is just, I mentioned, Professor Baogeng Shen, a academician in China. I serve as the Secretary General. There are more 5 deputy directors. Yeah. Here is me. Here is Professor Baogeng Shen. Yeah. Since the setup of this committee, each year we hold the annual conference on the calorics. So actually in China, there is a large team focused on calorics and application. And this is the announcement of the caloric conference this year. Actually, the annual conference will be held next month in Xiamen city in the south of China. However, currently the conference, the language is still Chinese. Maybe in future we hold the international conference. And next, I briefly introduce the location of our institute. Here is our institute. Our institute is located in the downtown of Beijing, nearby the famous Tsinghua University and the Peking University, just two blocks from our institute and very nearby. And our institute has 11 divisions. Our group belongs to the State Key Laboratory of Magnetism. Our laboratory have 6 groups. Our group is number 3. In our group, we have about 3 directions. One is the permanent magnets, one is the caloric material and energy conversion, and another is the oxide spintronics. And this is a team member in our group. This is Professor Shen. We totally have 8 staff, and there are 25 PhD students and postdocs working together with us. We also have 3 professors and 4 associate professors working in different directions. And today, I mainly talk about the application of cooling for the calorics. Cooling is everywhere. All the people know cooling. However, the conventional cooling technique encounter many problems, such as environmental and efficient problem. According to the United Nations program, uh, the cooling account for the 25 up to 30% of the energy consumption. So there is an urgent need to develop the novel cooling technology. One promised choice is the cooling technology based on caloric effect. Yeah. Compared to the conventional cooling technique, the caloric cooling has many advantages. The, the material is non-toxic solid rather than the toxic gas. They also have a high efficiency. The efficiency can be as high as 60%. Among all the calories I just mentioned, the magnetic cooling based on the magnetocaloric is one of the longest studied. These scientists use gadolinium-based paramagnetic materials and achieve temperature lower than 1 Kelvin. Due to this achievement, these scientists win the Nobel Prize in 1949. And currently, magnetic cooling is still an important means to achieve the ultra lower temperature. Ultra lower temperature has many important applications, such as scientific research and deep space exploration. And what's the basic requirement for the low temperature materials? According to this equation, the basic requirement is a large momentum. And here G denotes the total angular momentum quantum number. So if the materials have a large entropy change, we hope the material has a high momentum. Yeah, but we also hope the material has a lower ordinary temperature. According to this equation, that means the material has the weak magnetic interaction. We also hope the material can be easily magnetized. So that is, the material should have the weak magnetic anisotropy. The weak magnetic anisotropy means actually the momentum from the total momentum comes from the coupling between spin and the orbital. The weak magnetic anisotropy require the orbital contribution as small as possible. At the best, the contribution is 0. And another requirement is a high magnetic density. So this picture shows the gadolinium-based low-temperature refrigerants. The gadolinium ions with 3 valence just meet the requirement I just mentioned. The spin quantum number is 7/2, while the orbital quantum number is 0. So many people pay attention to the gadolinium-based material. And this picture summarizes the gadolinium-based materials one can find in the shadow area. All of the shadow area, the material is a gadolinium-based material. One can find the ordinary temperature around the 1 Kelvin. But the experimental entropy change is still lower compared to the theoretical value. So to enhance the entropy change, we turn to the EU-based materials. I mean the EU ion with 2 valence. For the EU element with three valence, there are no the momentum as zero. But when the valence is true, actually the spin quantum number and the orbital quantum number is the same as the gadolinium ion with three valence. So the first material come to our site is uranium dihalides like this. However, also for the material with F, the material has a high magnetic ion density, but this material, the ground state is antiferromagnetic, and the antiferromagnetic state is insensitive to magnetic field. So we choose this one, the EU chlorine. This material, the ground state is ferromagnetic and sensitive to the external magnetic field. And this compound actually has a very simple structure. And the measured shortest UU distance by XRD is larger compared to the other EU-based magnetocaloric materials. And this behavior promotes the spin, the free iron behavior of the EU ions. Yeah, so this picture shows the DFT calculation result. This is dose map, and this is ELF, the electron localization function map. From these two results, we can find that there are little hybridization between EU and chlorine. Moreover, we also make some theoretical calculations. We use based on the free Heisenberg spin model. We calculated the MH curve. One can find the measured curve agree well with the theoretical curve. And this result further proves the nearly free iron behavior of the EU ions in the compound. And this behavior bring about the large entropy change. And this is the theoretical value according to this equation we found at the 5 Tesla. The measured entropy change can account for a very high percent, about 96%. And this is a comparison of our material with other materials. One can find at 1 Tesla, the entropy change is even larger than the commercial materials. GGG is about 2 times larger than the GGG and at 2 Tesla. At 5 Tesla, the entropy change has also exceed all other reported materials. We also performed the adiabatic demagnetization refrigeration measurement. Actually, for the low temperature materials, there are 2 parameters for evaluation the performance of the materials. One is the lower risk temperature, another is the holding time at the lower risk temperature. So use our material as the refrigerant. The lower risk temperature can be up to this value. Also, the temperature is still somewhat higher than other materials, but the holding time at any initial conditions is over 1 hour, and this character is better than any other material, including this is a commercial material, and these 3 are the commercial material, and this material is just published last year by a group in our institute, published in Nature. So our materials, the holding time, this character is even better than this one. So besides the low temperature cooling, people are more interested in the room temperature cooling technology. And this is a drink cooler based on the magnetocaloric effect. And this cooler is displayed in the in last year in a conference in Germany. I attended the conference. To show the size of the cooler, I take a picture with the cooler. And currently, this cooler has been sold in the supermarket. Yeah, and this is a drinking cooler based on the barocaloric effect. This cooler is displayed in the catfish day on caloric hold in last year. And this cooler is still in the laboratory, not go to the supermarket. For the room temper material, the most attention people paid is lithium ion silicon materials. When I was a PhD student about 20 years ago, our group discovered these materials. There were more than 200 groups follow our study, and many countries and many people use the materials in the machine. Due to this achievement, due to the discovery of this material, our group also win several awards in China. And many people use the material in the machine. The best user is the Astronautics Center of the United States. They use the 6 layers of the lithium silicon-based material with different PC as a refrigerator. The cooling capacity can be as high as 2.5 kilowatt and 11 Kelvin spin. This is also the largest cooling capacity based on the magnetocaloric effect so far. And this slide shows our recent work about the regulation of phase transition and magnetocaloric effect. We discovered the laser iron silicon materials, so we also like this material very much. So through introduce pressure in this material, through introduce pressure to influence the lattice order, the entropy change can be enhanced by twice. For this material, the holding copper silicon material, this material has a very complicated spin structure. Through introduce the pressure to influence the spin structure, the entropy change can be largely enhanced. The enhanced ratio can be as high as 150%. And this is another magnetocaloric materials, the iron rhodium. This material has a very big drawback, is large hysteresis loss. We glue the film onto the PMNPT through introduce the non-volatile strain, and we achieved the non-volatile reduction of the hysteresis loss. We also achieved the adjustment, the dynamic adjustment of taper strain by introduce the metal field of magnetic field and electric field. And this work is cooperated with Dr. Professor Adler. We, in these materials, the iron rhodium magnetocaloric effect, through introduce the second phase, the cycle stability can be largely enhanced. And this is our recent work focused on the less iron synthetic materials. Also, this material has been focused on more than 20 years. The addition of cobalt can enhance the cool temperature, can also enhance the mechanical properties, but the underlying mechanism is unclear. The main reason is that the people don't know the location of cobalt in the structure. And this is the structure of the compound. Actually, in the structure, the iron has two positions, one in the center, one is outside. People don't know whether the cobalt like to occupy the central one or the outside one. Because the iron and the cobalt has a similar atomic radius, X-ray has no way to distinguish these two. So we use the joint strategy of XRD and neutron diffraction and determined the occupation of cobalt. Actually, the cobalt likely to occupy the central position. And based on the result, we performed the electric structure calculation and ELF and explained the mechanism of the enhanced mechanical properties. We also studied the caloric effect for the ferric materials such as the ferromagnetic, ferroelectric, and ferroelastic materials. There is a natural correlation among the spin, lattice, and polarization. For example, for materials with strong spin, lattice coupling, the application of magnetic field can produce the magnetocaloric effect, and the pressure can induce the barocaloric effect. And when the both field, I mean, when the magnetic field and pressure was simultaneously applied to the materials, there will another extra term, which called the coupled caloric effect, will appear. And this is a single barocaloric in the single magnetocaloric effect. And this is an extra term. Actually, this extra term is the double weighting of this function. So we choose Hughes alloys, the nickel manganese, indium with rich manganese as a model and studied the coupled caloric effect. And in the structure, the excess of manganese occupied the site of indium. So the shortest manganese distance even smaller than the critical distance of artifact magnetic. Due to this character, the transition can be driven by either magnetic field and pressure. So by modulating the cross-coupling function between spin and lattice, the barocaloric entropy change can be largely enhanced. And this picture shows the modulation of magnetic field and pressure on the coupled caloric effect. And this column shows the barocaloric entropy change contributed by the coupled caloric effect. One can find at low pressure, the modulation of magnetic field on the barocaloric effect is nonlinear. But when at a high pressure, the modulation will become linear. We also studied, we also did some research on the barocaloric effect. People know the entropy consists of four terms. And when these two terms, I mean the lattice ordering and the conformation order of the organic chains. I mean, when these two term plays the dominant role on the entropy, the material will show the large barocaloric effect. In the year of 2019, Professor Li Bing, a Chinese scientist, reported the colossal barocaloric effect in plastic crystal. And the entropy change is very huge. It's about one order larger than the conventional materials. However, this material usually has a very wide hysteresis loss. For example, this material shows the high risk entropy change, but the hysteresis loss can be as wide as 60 Kelvin. Because of the huge hysteresis loss, the reversible entropy change is approach zero, even a large pressure applied. So to reduce the hysteresis loss, we turn to the two-dimensional materials. The first material come to our site is this one. This is the molecular formula. The organic and inorganic layered perovskite. Yeah, compared to the three-dimensional organic materials with all hydrogen bonds, the two-dimensional materials have weak one-way connection in one direction. One can find the entropy change is still large, but the hysteresis loss can be as small as 2.6 Kelvin. As a result, we can achieve the large reversible entropy change at a very small pressure. At the pressure here, 1.1 GPa, the entropy change is larger than in other materials. Moreover, in the three-dimensional materials, we introduce the non-organic chains to construct a two-dimensional one-way structure. We achieved much larger reversible entropy change. The molecular formula like this. This is the structure of the molecular. Originally, the nitrogen atom is bonded with 4 hydrogen. On the left and the right, we use the organic chains to replace the hydrogen. Then the two-dimensional structure can be constructed. One can find the entropy change is still remain large, but the hysteresis loss can be reduced to about 6 Kelvin. And this is the result of XRD. We can find across the transition there is a large change of volume, but the change of volume mainly focus on the CX. I mean, the AB plan keeps nearly unchanged. The CX is here, so the extension of CX provide enough space for the movement of the organic chain. So the material still remains a large entropy chain. From this picture, we can find when the 3D materials was constructed to the 2D materials, the disappeared caloric effect can be recovered, when the materials was turned to the 2D structure. This picture summarizes our recent work on the magnetocaloric effect, barocaloric effect, and the electrocaloric effect and the device. And these two work I have talked just now, and I also briefly introduce our recent work just published later this year about the electrocaloric effect. Actually, the electrocaloric effect is not new, has also have a long history. The first time of the first appearance of this word as about at the year of 1940s, but the area of the electric color effect keeps silence until the discovery of the giant electrocaloric effect in the PVDF polymer. This material shows a very huge entropy change, but the driven field is also huge. For the inorganic perovskite materials, also the driven field can be small. The entropy change is also small. So we use the organic and inorganic hybrid strategy. We achieved the giant electrocaloric effect driven by a small electric field. I don't say more about this work because due to the time limitation. If people interested, you can read this paper here. Moreover, I also give a very brief introduction of the device, and we also constructed the first full solid state magnetic cooling device based on the new principle of the hybrid refrigeration. The cooling area capacity surpassed that of the previous reported other devices. And this work published last year. The citation up to now is 19 times. I mean, many people read this paper. That means the device is very useful. Moreover, this device, besides cooling, this device has this device can be used for the thermal management. From this picture, one can find the heat transfer coefficient is higher than both air by 3 times. This is our device, and this is the forced air, the convection. Okay, at last, I talk about the collaboration between China and Russia. Actually, our group cooperated with this Institute of Physics of Dagestan, scientists of Center Russia of Academy of Sciences, about 6 years. We call these two Professor Adler, who attended our the room meeting, and another is Olive. In the past 7 years, we visited each other for several times. We also achieved a lot of interesting results. We briefly introduced 2 examples. And this example is just published this year, and this work focus on the high entropy alloys for the materials of R here, the R cobalt, yeah. And in the in the R side, we introduce the high entropy. That means I introduce the configuration entropy. The configuration entropy will introduce the lattice distortion. And this is the high resolution TM result. We can see the lattice, the lattice distortion. We studied the influence of the lattice distortion on the static and the dynamic performance of the magnetic caloric performance. Actually, for the high entropy alloys, I mean this composition, the transition nature is the second order in nature, and this one, the dy column is the first order, the first order transition. Also, this one shows the second order transition, and they have a very the delta T, I mean the magnetocaloric effect, shows a high dependence of the frequency. At the low frequency, lower than 5 hertz, the dependence on the frequency is similar. I mean this one and this one. But at the high frequency, the delta T go down sharply. The reason is the introduced lattice distortion. This is another cooperating work published 3 years ago, focused on the iron rhodium magnetocaloric effect. This material is also a well-known magnetocaloric materials, but the main problem is a large hysteresis loss as the bad cyclic stability. And this is the main phase, the R, the iron rhodium, and this is the main phase. We introduce the second phase, namely gamma iron rhodium. We found the cycle stability can be largely enhanced. Okay, that's all. This is the team member and our student, and this is my contact information. Welcome the Russian scientist with me, visit Beijing. Thank you very much. Thank you for your attention.